I want to start today by putting a philosophical question on the table, or maybe it's more of a confession. Why are we, as a species, so utterly obsessed with shiny things?
hmm
It's a strange phenomenon when you actually stop and, analyze it. You're walking past a jewelry store window, or you're hiking and you see sunlight hitting a piece of quartz in the dirt, and something in your brain just goes bing. It demands your attention. It's like we all have this inner magpie that we can't quite shut off.
It is a universal human experience. And frankly, you are not alone in that feeling. It turns out that this obsession with gems, with glitter, with brilliance, it isn't just vanity.
Right.
It isn't just about showing off wealth or status,
Or
although those things certainly play a part later on. But the root of it, it goes much, much deeper. The source material we have today suggests it is actually biological. It's hardwired.
See, that's where it gets interesting for me, because usually when we buy a sparkly ring or a gold chain, we tell ourselves it's an aesthetic choice. We think, oh, I have good taste, but you're suggesting that my need to buy that ring is actually a command written into my DNA. Like I can just blame evolution for my credit card bill.
To a significant extent, yes, you can. We have some fascinating research here, specifically looking at the neuroscience of beauty. It centers on a small but incredibly powerful cluster of neurons in the brain called the ventromedial prefrontal cortex, or the VMPFC for short.
Okay, let's unpack this because I was reading the study in the notes and it blew my mind. The VMPFC isn't just the ooh pretty thing center, is it? It's doing something much more complex regarding how we process value.
Exactly. The VMPFC is the part of the brain responsible for assigning worth to objects and determining the depth of your emotional attachment to them. It helps you decide, is this valuable to me?
Okay.
But here's the kicker, and this is where the wires get crossed. The same region plays a vital role in your assessment of morality.
Morality. So you're saying the same part of my brain that decides if a person is good or kind is also deciding if a diamond is pretty.
Yes, this is the biological basis of what psychologists call the halo effect. When we behold something truly beautiful, like a glowing, shining jewel that VMPFC lights up like a Christmas tree, it spins our moral compass. It actually impairs our judgment.
Impairs it? How?
We subconsciously infer that because this object is beautiful, it must also be good or benevolent. Simultaneously, and this is the dangerous part for your wallet, it stimulates the motor cortex.
But the motor cortex, that's the part that controls physical movement, like reaching for something.
Precisely. So neurologically speaking, when you see a gem, you are literally compelled to reach out and take it. It's not a passive observation. Free will be damned, as one of our sources puts it. Your brain is shouting, grab that, while simultaneously suspending the part of your frontal lobe that asks, wait, is this a financially sound decision?
That explains so much about impulse shopping. It's a neurological hijacking. But the question remains, why? Why would we evolve to have a grab the shiny thing button in our brains? Evolution usually selects for survival traits, not, interior decorating.
Right. And the leading theory is what we might call the sparkle equals life theory. Think about it. For our ancient ancestors on the African savanna, what was the most critical, immediate resource for survival?
It has to be water. You can survive weeks without food, but only days without water.
Right. And how do you spot fresh, clean water from a distance in the bright sun?
It shimmers. The sun hits the ripples on the surface. A stagnant, muddy, disease-ridden pool doesn't sparkle. A fresh, moving stream does.
Exactly. We evolved to spot shimmering, glittering surfaces because that meant water, and water meant life. Our instincts learned to value that glitter above almost anything else. It was a core survival mechanism.
Wow.
So fast forward a few 100,000 years, and we have transferred that survival thirst onto diamonds, gold, and rubies. We are still hunter-gatherers. We're just hunting for ice in a very different sense.
That is profound. We're basically just really thirsty apes looking for a drink, but we've ended up building an entire global economy around the crown jewels.
In a way, yes. And that is the mission of this deep dive. We are looking at a massive stack of research, specifically drawing from the Smithsonian's definitive guide on gems, geological surveys, and historical analyses to understand this obsession. But the thesis here is that gems aren't just pretty rocks. They're a map and a codex.
A codex to history. What do you mean by that?
Precisely. If you look at human history, every age is effectively the Stone Age. From the first chieftain who put a shiny shell on his head to the silicon chips in our computers, which are just purified sand, really, our entire story is written in stone.
Huh. I never thought of it like that.
So today, we're going to learn how to read that story. We're going to cover the geology, the atomic chemistry, the intense physics of the cut, and the often bloody history behind these stones.
I love it. We're going from the atomic level all the way to the auction house. So let's start at the very bottom. What actually is a gem? Because I feel like most people, myself included, use the words rock, mineral, and gem interchangeably, but scientifically, those are three very different things.
You are right, they are very distinct, and it's a great place to start. Let's begin with the fundamental building block, the mineral.
Okay.
A mineral is a naturally occurring solid with a specific chemical composition and a distinctive crystal structure. It is defined by its atoms.
Okay, so it has a strict recipe, a chemical formula.
A very strict recipe. If you change the ingredients or the structure, it becomes a completely different mineral. For example, graphite. The stuff in your pencil is pure carbon. Diamond is also pure carbon. Chemically, they are identical twins. But the structure, the way those carbon atoms are bonded together, is completely different. So they are different minerals with wildly different properties.
One is super soft and gray. The other is the hardest thing we know and brilliantly clear just because of the atomic arrangement.
That's the power of structure. Now, a rock is different. A rock is an aggregate of minerals.
I like the analogy I saw in her notes, the cookie analogy.
It works perfectly. Think of a chocolate chip cookie. The cookie itself is the rock. But the flour, the sugar, the chocolate chips, those are the minerals. You can have a rock that is mostly one mineral, like limestone, which is mostly calcite, or a rock that is a complex mix of many, like granite.
So granite is the cookie, and the little specks of quartz, feldspar, and mica that you see inside it are the ingredients, the minerals.
Exactly. Now, a gem is a specific elite subset of minerals. To be a gem, a mineral usually has to meet three criteria: beauty, durability, and rarity. And usually, though not always, it has been cut and polished by a human.
Beauty, durability, rarity. So not every mineral gets to be a gem. Halite is a mineral, it's just rock salt. But we don't put it in engagement rings because it dissolves in water, and it's definitely not rare.
Right. There are over 5,000 known minerals on Earth, but only a fraction of those, maybe 100 or so, are consistently considered gems. And just to make things complicated, there are outliers.
Of course. There are always outliers.
We have what are called native elements. These are minerals made of a single element on the periodic table. Most minerals are compounds, a mix of elements, but native elements are pure.
So that's things like gold, silver.
Gold, silver, copper, platinum, and yes, diamond, which is just pure carbon. They are the elemental aristocrats of the mineral world.
And then you have the things that aren't stones at all, right? The organic gems.
Correct. These are the rebels of the gem world: pearl, amber, jet, coral. They are biological in origin. They don't come from the Earth's crust in the same way.
Amber is tree sap, basically.
Fossilized tree resin, yes. And a pearl is a biological defense mechanism from a mollusk, essentially an oyster fighting off an intruder like a grain of sand by coating it in layers and layers of nacre. They aren't crystals, they don't have a geometric lattice, but we prize them just as highly for their beauty and rarity.
It's interesting that we lump them all together in a jewelry box, even though one came from a tree and one came from a volcano, which brings us to the source. Where do the actual stony gems come from? They don't just appear.
They are born in the rock cycle. And born is perhaps too gentle a word. It's a violent, chaotic birth. You have three types of rock factories, or three processes, really.
Right.
First, igneous. This is fire. This is rock that started as magma or lava and cooled down. That's where you get your granite, and often where diamonds are brought to the surface.
Right, diamonds are formed deep in the mantle, right? They just use the magma as an elevator.
A very, very fast elevator. They form under immense pressure. We're talking gigapascals of pressure, about 100 miles down in the Earth's mantle. Then these very specific violent volcanic eruptions called kimberlite pipes shoot them to the surface at supersonic speeds.
Supersonic?
Yes. If they came up slowly, the change in pressure and temperature would cause their atomic structure to rearrange. They would turn into graphite, they'd turn into pencil lead. They need that violent, rapid ascent to lock their crystal structure in place and stay as diamonds.
That is wild. So every diamond is a survivor of a supersonic volcanic eruption. Okay, what's the second rock type?
The second is sedimentary rock, which is essentially the product of erosion. Wind and water grinding down other rocks, carrying the particles, and letting them settle in layers over millions of years, compacting under their own weight.
Like sandstone or limestone.
Exactly. And some gems form here. Opal is a great example. It forms from silver-rich water seeping into cracks and voids in sedimentary rock over a long, long time. And finally, you have metamorphic.
Metamorphic. That means changed, right?
It does. This is where things get really intense. You take an existing rock, igneous or sedimentary, bury it deep in the Earth's crust during, say, a continental collision, and subject it to insane heat and pressure, a tectonic trash compactor, until it changes into a new rock.
Mm.
Limestone gets crushed until it becomes marble.
And that's where rubies and sapphires come from.
A lot of them, yes. That intense pressure and heat can rearrange the atoms of the original rock, bake out impurities, and allow new, dense, durable crystals like corundum, which is ruby and sapphire, to grow.
So gems are basically the beautiful survivors of this geological torture chamber.
That is a very apt way to put it. They are the few that survive the heat, the pressure, and the erosion. And when they survive, they usually form as crystals. This brings us to crystallography.
Which sounds intimidating, but looking at the notes, it's actually just geometry, right? On an atomic scale.
It's simpler than it sounds. Remember, we said minerals have a specific structure. That structure is built on what's called a unit cell. Imagine a single Lego brick. That's your unit cell. It contains the specific atoms in a specific arrangement. Now imagine stacking those Lego bricks in a perfect repeating pattern in 3 dimensions. Billions and billions of them. That is a crystal.
So the shape of the gem we dig out of the ground, the habit, as the sources call it, is determined by that tiny atomic Lego brick.
Precisely. It all starts in the atomic level. If the unit cell is a cube, the crystal will tend to grow in a cubic system. Think of pyrite, fool's gold, which forms these perfect little cubes. If the unit cell is a hexagon, it grows in a hexagonal system, like an emerald or an aquamarine crystal, which are these beautiful 6-sided prisms.
So the macro reflects the micro.
Always. This dictates the habit of the stone, how it looks when it grows in nature unconstrained.
Habit is a great word for it, like it has a personality.
It does. Some have an acicular habit, which comes from the Latin for needle. They grow in long, thin, fragile needles. Others are botryoidal.
Botryoidal. I saw the picture of the malachite in the source material. It looks like a bunch of green grapes melted together. It's beautiful, but strange.
That's exactly what botryoidal means. From the Greek for bunch of grapes. It's not one single crystal, but countless tiny crystals radiating outwards, forming these bubbling globular shapes. Or you can have dendritic growth.
That's the one that looks like a plant.
Yes, like ferns or tree branches, but it's actually a mineral, usually a metal oxide like manganese, growing through the cracks in another rock, like an agate. A fossilized frost pattern.
It's amazing that nature just does this. It organizes atoms into these perfect geometric shapes without any help. It's the ultimate order emerging from chaos.
It is. And that order, that internal structure, is what allows us to identify them. Because once you dig up a crystal, how do you know what it is? A red stone could be a ruby, a spinel, a garnet, or just a piece of red glass.
Right. And you can't just taste it.
Please do not taste the rocks. This is the science of gem identification. And rule number 1 for a gemologist: don't just look at the color. Color is often the least reliable indicator.
Really? I would have thought that's the first thing you'd look at.
It's the first thing you notice, but many different minerals can be the same color, and one mineral can come in almost every color imaginable. So we have to test its physical properties. The most famous one is the Mohs scale.
Ah, yes, the scratch test. I remember this from high school geology.
Right, the Mohs scale of hardness. It ranges from 1 to 10. Number 1 is talc. You can scratch it with your fingernail. Number 10 is diamond, the hardest natural substance. But there is a massive, massive misconception here that we need to clear up.
Which is?
That hardness equals strength,
Yeah.
and that the scale is linear. It's neither.
Okay, break that down.
First, the Mohs scale only measures resistance to scratching. It does not measure toughness. And second, the scale is not like a ruler. The gap in hardness between 9, which is corundum ruby and sapphire, and 10, diamond, is greater than the entire gap between 1 and 9 combined.
Whoa, really? So diamond is in a league of its own.
Completely. It's exponentially harder than anything else. But that brings us back to hardness versus toughness.
Wait, there's a difference. I think most people assume if a diamond is hard, it's indestructible.
A huge difference. Toughness is resistance to breaking or shattering. A diamond is incredibly hard. You can't scratch it with anything but another diamond. But it is brittle.
Brittle.
Yes. Because of its rigid crystal structure, if you take a hammer and hit a diamond along what's called its cleavage plane,
It'll break.
it will shatter into 1,000 pieces. It is not tough. On the other hand, a piece of jade, specifically nephrite jade, is much softer than a diamond on the Mohs scale, only about a 6.5. You can scratch it with a quartz crystal.
Okay.
But jade has an internal structure of interlocking fibrous crystals.
Mm.
It is incredibly tough. You can hit jade with a hammer, and it'll just ring like a bell. That's why ancient cultures made axes and weapons out of jade, not diamond.
That is a crucial distinction. I feel like that saves someone from a very expensive experiment with a hammer. Honey, look how strong this engagement ring is. Smash.
Exactly. Never hammer your jewelry. Now, how it breaks is also a clue for identification. This is the concept of cleavage versus fracture.
Cleavage means it splits cleanly, right? Along a flat plane.
Yes, because of that atomic grid, the Lego bricks, some stones have planes of atomic weakness running through them. Diamond has perfect cleavage in 4 directions. One sharp tap in exactly the right spot, and it splits perfectly smooth. That's how diamond cutters work. They're exploiting the atomic weakness of the stone.
And fracture. That's breaking randomly.
Fracture is random breakage, yes. It happens when there are no weak planes, and the atomic bonds are roughly equal in all directions. But even fracture has different styles. The most distinct one is conchoidal fracture. Have you ever chipped a piece of thick glass or obsidian?
Yeah, it leaves those sharp, curved, shell-like ripples.
Exactly. That's conchoidal fracture. Quartz has it. Garnet has it. If your mysterious red stone breaks like that, it's likely a garnet or glass, not a ruby. Rubies don't have that specific shell-like fracture.
Okay, so we've scratched it, we've smashed it. Hopefully not. But what about the look? The wow factor, the physics of how it plays with light.
That's the optical properties. And this is where the magic really happens. First, you have luster.
Luster.
It's simply how light reflects off the surface of the stone. Most gems are vitreous, which just means glassy. But the heavy hitters, like diamond, have a luster we call adamantine.
Adamantine, that sounds like a superhero metal. Wolverine's claws?
It actually comes from the Greek adamas, meaning unbreakable or invincible. It refers to a hard, cold, brilliant shine that nothing else quite matches. It looks different, more brilliant than glass.
Okay.
Then, of course, there is color. And this is where the chemistry gets really fun. Some stones are ideogrammatic.
Meaning self-colored?
Exactly. Their color is an essential part of their chemical formula. Rhodochrosite is pink because it's made of manganese carbonate. Manganese is an essential ingredient, and it's what makes it pink. It can't be any other color. Malachite is green for the same reason, the copper in its formula.
But most gems come in rainbows, don't they? Like sapphires or tourmaline.
Most of the famous ones, yes. Those are allochromatic.
Other colored.
Right. They are pure minerals that have been polluted by tiny trace elements that aren't part of their essential formula. Pure corundum, which is the mineral for sapphire and ruby, is completely colorless. It looks like glass.
No way.
But if you add a tiny bit of chromium as an impurity doing its growth, maybe 1% of the atoms, it turns a vibrant red and you have a ruby. Add iron and titanium, it turns blue and you have a sapphire.
So the most valuable gems in the world are basically just contaminated crystals. That's wild.
In a sense, yes. We pay millions for the specific impurities. And then there's what the light does inside the stone. This is refraction. When a beam of light passes from air into a denser medium like a gem, it slows down and bends. The amount it bends is called the refractive index, or Ri.
And a higher Ri means more sparkle.
It means more brilliance, yes. It's a measure of how much the stone can bend light. But fire, that rainbow flash you see in a diamond, that's a related but different property called dispersion.
Okay.
Dispersion is the stone's ability to take white light and split it into the full spectrum, exactly like a prism on the cover of a Pink Floyd album. Diamond is famous for its very high dispersion. That's where the flashes of red, blue, and green come from.
And there's some special effects too, right? I was reading about something called pleochroism. Sounds complex.
Oh, this is a fun one. Tanzanite is the classic example. Because of its crystal structure, it absorbs light differently along different axes. So if you hold a rough tanzanite crystal and turn it in your hand, it literally changes color. From one angle, it looks a deep sapphire blue. From another, it looks a vibrant violet. And from a third, it might look reddish brown or even green. It's 3-colored.
So the cutter has to decide which color they want to emphasize. That's a huge responsibility.
It's a high-stakes geometry problem. If they cut the table of the stone along the wrong axis, you might end up with a less desirable brownish stone instead of a vibrant blue one. The value depends entirely on their choice.
And then there's the star effect. Asterism.
Asterism, yes.
Yeah.
This happens when you have tiny, microscopic, needle-like inclusions, usually the mineral rutile inside the stone.
Yeah.
And they have to be aligned perfectly with the crystal's axes of growth.
So it's a flaw, but a beautiful one.
A very organized flaw. When you cut the stone with a smooth dome as a cabochon, the light reflects off those parallel needles and creates a floating 6-rayed star that moves across the surface, Star rubies and star sapphires are incredibly prized for this.
It's like magic tricks, but it's just
It
physics.
is physics disguised as magic. All of gemology is really.
So we know what they are and how to spot them, but where do we find them? I have this image of just wandering into a cave and finding a pile of emeralds, but I'm guessing it's not that easy.
Sadly, no. The geography of gems is fascinatingly specific. It's like a global treasure map. And it's dictated by those violent geological events we talked about. Certain conditions have to be met for certain gems to form.
So where are the hotspots? What are the famous locations?
Well, if you want emeralds, you go to Colombia. The mines there, like Muzo and Chivor, produce around 70% of the world's emeralds and certainly the finest quality.
70%, that's a near monopoly.
It dominates the market. And it's because of the unique geology there. Sedimentary host rocks that were twisted and heated by the Andes Mountains rising. If you want rubies, historically you go to Myanmar, which used to be Burma. The Mogok Valley there produces about 90% of the world's finest pigeon blood rubies.
Pigeon blood.
It's a trade term for the most desirable color of ruby, a pure, vibrant red with a hint of blue or purple for opals. It used to be almost exclusively Australia. 95% of the supply from places like Cooper Pedy and Lightning Ridge.
And diamonds. That's Africa, right?
Africa is still the heavyweight, producing about 65% of the world's diamonds, specifically nations like Botswana, the DRC, and South Africa. But we're seeing more from Russia and Canada now, too, with some very high-quality deposits. And for sapphires, you have hotspots like Madagascar, Sri Lanka, and historically, Kashmir.
And how do they get them out? Is it all just pickaxes and dynamite?
There are two main ways. One is hard rock mining, or primary deposit mining. This is digging tunnels or massive open pits to get to the original veins or pipes where the crystals formed. This is expensive, dangerous, and requires massive industrial scale. This is how most diamonds are mined.
And the other way.
Placer deposits or secondary deposits. This is nature doing the hard work for you. Remember we said rocks erode? Well, when the host rock erodes away over millions of years, the heavy, durable gems like rubies, sapphires, and diamonds get washed down into the rivers. They settle in the gravel beds because they are heavier than the surrounding sand and dirt.
So that's like panning for gold. You sift through the river gravel.
Exactly. You sift through the river gravels, often by hand. It's safer and cheaper, which is why it's often done by artisanal miners individuals or small groups working with basic tools. But we have to talk about the yield. This is where the economics get staggering.
The yield, you mean how much they actually find versus how much do they move?
Yes. Mining gems is incredibly inefficient. You might move tons and tons of earth to find a handful of stones. For diamonds, a typical kimberlite pipe might yield 1 carat of diamond for every ton of rock mined.
1 part per million, basically.
Or even less. And even when you find them, most of them are garbage from a jewelry perspective. Only about 30% of the diamonds mined worldwide are actually gem quality.
And the other 70%?
They're called bort, or industrial-grade diamonds. They are gray, opaque, heavily flawed, and ugly. But they're still super hard, so they end up on drill bits and saw blades and in abrasives.
So if I dug up a dump truck full of diamond-bearing rock, the vast majority of what I find is just really hard gravel.
Pretty much. It makes you appreciate the ones that end up in a jewelry store even more. They are the top 1% of the top 1%. True freaks of nature.
Speaking of the jewelry store, stones don't come out of the ground looking like they do in a ring. They come out looking like, well, rocks. Usually greasy, oddly shaped pebbles.
Right. They are rough. They often look cloudy, dull, and misshapen. The transformation happens in the hands of the lapidary, the gem cutter. This is the art of the cut, and it is a destructive art.
Destructive? How so?
To create a beautiful faceted gem, you have to destroy the rough. You grind it away. You lose a significant amount of the stone's original weight, sometimes 50% or even 60% or more, just to get the perfect shape and brilliance. Imagine buying a block of gold and filing half of it into dust just to make it look pretty. That's what cutting is. It's a huge financial gamble for the cutter.
I think we need to define the anatomy of a cut stone because there are terms I hear but don't quite get, like table or pavilion.
Absolutely. Think of a standard round diamond. The very top flat facet is the table. It's the main window into the stone. The top section sloping down from the table is the crown.
Like a little hat on the stone.
Exactly. Then there's the girdle, the widest part, the belt of the stone. That's usually where the metal setting holds it. Below the girdle is the pavilion, the bottom cone that comes to a point. And right at the very tip of the bottom is the cullet.
The cullet, is that just a sharp point?
Ideally, it looks like a point from above, but usually it's actually a tiny flat facet. If it were a perfect sharp point, it'd be too fragile. It would chip the second you tried to set it. So they flatten it just a microscopic amount for durability.
That's smart. And the style of cutting changes the whole look, right? We have the brilliant versus the step cuts.
Completely different philosophies. The brilliant cut, like the classic round diamond, has these triangular and kite-shaped facets radiating out from the center. It was mathematically perfected by a mathematician named Marcel Tolkowski in 1919.
He did the math on sparkle.
He calculated the exact angles needed for the crown and pavilion so that any light entering the stone through the top would bounce off the internal walls and shoot right back up at the eye. It is an optical machine designed to maximize sparkle.
Versus something like an emerald cut, which looks like a hall of mirrors.
Right, the step cut or emerald cut. These have long rectangular facets that look like a staircase. This doesn't sparkle as much. It doesn't create that glittery effect. Instead, it creates broad, dramatic flashes of light.
What's the point of that, then?
It's less about bling and more about showing off the purity, the clarity, and the deep color of the stone. It's an unforgiving cut, though. If there's a flaw inside, a step cut will put a spotlight on it.
So you need a really clean, high-quality stone for an emerald cut. And what about the cabochon? That's the smooth, domed one with no facets.
The oldest cut in the world. Just a smooth, polished dome. We use this for opaque stones like turquoise or jade, where faceting wouldn't do anything. Or, as we mentioned, for those special phenomenal gems like the star ruby, you need that smooth dome to focus the light and create the star.
And then you have carvings. I was struck by the cameos and intaglios in the visual guide.
Those are miniature sculptures. Cameos are relief carvings. You take a material with layers of different colors, like a banded agate or the seashell, and you carve away the top layer to leave a raised image, like a white portrait against a dark background. An intaglio is the opposite. You carve the design into the stone.
Like a signet ring for making a wax seal.
Exactly. It's an ancient art form.
So we've mined it, we've cut it, we've thrown away 50% of it in dust. Now we have to sell it. How do we determine what it's worth?
We all know the 4 Cs.
The 4 Cs. The marketing genius of the diamond industry, specifically De Beers, but the principles apply to most gems. Color, clarity cut, and carat weight. Let's run through them, but focus on the money aspect. Color. We talked about the chemistry. For most stones, more intense is better.
Generally, yes. You want a vivid, pure, saturated color. A pale, washed-out ruby is just a pink sapphire, and it's priced accordingly. A dirty, brownish-green emerald is cheap. But clarity is interesting. This refers to inclusions, the flaws inside.
And we want flawless, right? The cleaner, the better.
Ideally. But it depends on the stone type. This is where gemologists get into type 1, type 2, and type 3 gems. A type I gem, like an aquamarine or a blue topaz, grows in relatively calm geological conditions. It is expected to be clean. If an aquamarine has visible flaws, its value drops off a cliff.
But emeralds, you always hear about inclusions in emeralds.
Emeralds are the classic type 3 gem. They're almost always included. As we discussed, they grow in chaotic, violent hydrothermal environments. A completely flawless emerald is a freak of nature and astronomically expensive. So we tolerate the garden, the jardin as the French say, in an emerald much more than we would in a diamond. An emerald with some inclusions can still be worth millions if the color is top tier.
That's forgiving. Now, carat. This is the one people confuse with size all the time.
Yes. A carat is a measure of weight, not size. 1 carat is exactly zero point 0.2 grams. Think of a standard paperclip that weighs about a gram. So a 5-carat diamond weighs the same as 1 paperclip.
That really puts it in perspective. But the price doesn't scale linearly, does it? A 2-carat diamond isn't just double the price of a 1-carat diamond.
Oh, absolutely not. It's exponential. Because a gem-quality 2-carat stone is much, much rarer than a 1-carat stone. This brings in the unspoken 5th characteristic rarity. If a 1-carat diamond of a certain quality is, say, $5,000, a 2-carat diamond of the exact same quality might be $20,000 or $30,000.
Wow, and there are magic numbers, right, in the market.
Yeah, the price jumps disproportionately at the full carat and half-carat marks. A 0.99-carat diamond is significantly cheaper than a 1.00-carat diamond, even though you cannot tell the difference with the naked eye. The market pays a premium for the number 1.
Now, here's where it gets really tricky for the consumer. Synthetics and simulants. What's the difference? Because people just use the word fake to describe both.
This is a crucial distinction. A synthetic gem is the real deal, chemically and physically. A synthetic ruby is corundum with chromium. It's just grown in a laboratory in a few weeks rather than in the earth over millions of years. It has the same hardness, same optics, same chemical formula.
And a simulant?
A simulant is an imposter. It
Yeah.
just looks like the real thing. It's red glass or red plastic or cubic zirconia pretending to be a diamond or ruby. It doesn't have the same properties. It will scratch easily. It will dull over time.
So synthetic is a clone, simulant is a costume.
That's a perfect analogy. And then we have the fine print of the industry, treatments and enhancements. This is the industry's not-so-dirty little secret.
The cheat codes.
The cheat codes.
Yeah.
The truth is, almost every colored gem you see in a mall jewelry store has been treated in some way to improve its appearance. It's standard practice.
Like what? What are they doing to them?
The most common is heat treatment. Very common for sapphires and rubies. You take a cloudy pale stone, you bake it in a special oven at very high temperatures, and the color can deepen, and the clarity can improve. It's stable, it's permanent, and it's completely accepted in the trade, as long as it's disclosed.
And tanzanite you mentioned.
Tanzanite is a great example. It comes out of the ground as a sort of muddy, brownish purple color. They heat it to about 600 degrees Celsius, and it turns that gorgeous violet blue. Without heat treatment, there wouldn't be a tanzanite market.
And emeralds. I heard they get oiled.
Yes. Oiling or fracture filling. Remember those cracks and inclusions, the jardin in an emerald? They soak the stones in cedar oil or modern resins. The oil seeps into the tiny surface, reaching cracks, and fills them. Because the oil has a similar refractive index to the emerald, the cracks become much less visible. It dramatically improves the clarity.
But the oil can dry out over time, right?
Yeah, it can. It's not always a permanent treatment. That's why you have to be careful with emeralds. You should never put them in an ultrasonic cleaner because it will shake the oil right out, and you'll be left with a very different looking stone.
So you have to re-oil your emeralds, like changing the oil in your car.
Essentially, yes, every few years. Then there's irradiation.
That sounds intense.
It is. They bombard stones with radiation neutrons or electrons to change the color. That's how we get most of the vibrant blue topaz on the market. It starts as colorless or pale topaz. They zap it in a nuclear reactor or linear accelerator, and it turns blue.
It sounds a bit sci-fi.
It is high-tech chemistry applied to ancient rocks. And again, as long as it's disclosed, it's considered acceptable. The problem is when these treated stones are sold as natural and untreated at a much higher price. That's fraud.
We've talked a lot about crystals, but we have to dedicate some serious time to the heavyweight champion of the jewelry world. Gold. It's not a gem, it's a metal, but it is the frame for almost all of them.
Ah, gold. The native element, the metal of the gods. The sun solidified.
Why do we love gold so much? Aside from it being shiny, I mean, we've based entire currencies on it. We've fought countless wars for it. Why this specific metal over all others?
Chemically, it is unique. It is incredibly inert. That means it doesn't react with other elements. Iron rusts because it reacts with oxygen. Copper turns green. Silver tarnishes black.
Gold does nothing.
Gold does nothing. You can leave a gold coin at the bottom of the ocean for 1,000 years, like on a sunken Spanish galleon, and when you bring it up, it looks exactly the same as the day it went down.
So it represents immortality, eternity.
Precisely. In a world where everything decays, wood rots, iron rusts, people die, gold remains. It is the closest thing to eternity we can hold in our hands. Plus, it's incredibly dense and extremely malleable.
Malleable meaning you can shape it easily.
More than any other metal. You can hammer it, stretch it, mold it. 1 single ounce of gold can be hammered into a sheet that covers 100 square feet or stretched to a wire 50 miles long. It's almost magical.
That is mind-blowing. But that softness is also a problem for jewelry, right? Pure gold 24 karat is too soft to wear every day.
Correct. If you had a ring made of pure 24K gold, you could bend it with your fingers. It would scratch and dent instantly. So we mix it with other metals. We create alloys. This is where the carat with a K comes in.
Yes, not to be confused with carat with a C, which is weight. Carat with a K is purity.
Right. It's a system based on fractions of 24. 24K is 100% pure gold. 18K means it is 18 parts gold and 6 parts other metals. 14K is 14 parts gold, 10 parts other.
And the other metals are what make it stronger and also determine the color?
Exactly. If you want classic yellow gold, you mix it with silver and copper. If you want white gold, you mix the gold with the white metals like silver, nickel, or palladium. If you want rose gold, you add a higher proportion of copper. The copper gives it that warm reddish hue. There's even blue gold, where you mix it with iron or indium.
I didn't know blue gold was a thing.
It's very brittle and hard to work with, so it's rare, but it exists. It's all about the metallurgy, the art of the alloy.
The history of gold is just insane. The source material mentions the Mycenaean brooch from 1600 BCE. That's 3,600 years ago.
This is a stunning example of ancient mastery. 3,600 years ago, artisans were creating intricate gold work using techniques like granulation and filigree that rival anything we can do today. But I want to highlight the Roman snake armlet found in Pompeii.
The Pompeii one is haunting.
It was found on the arm of a woman who was trying to flee the eruption of Vesuvius in 79 AD. The volcanic ash buried her and preserved the gold perfectly. It's a snake coiled around her arm. The craftsmanship is incredible. Every scale is detailed. It has jeweled eyes. Its body is flexible. It shows that even in the face of the apocalypse, this was one of the things she tried to save. Her wealth, or perhaps her talisman.
Gold really does carry the weight of history. And speaking of history and gold, we have to talk about the woman in gold, the Gustav Klimt painting. It's not jewelry, but it is perhaps the most famous use of gold in modern art.
Gustav Klimt's portrait of Adele Bloch-Bauer I. This is a story that encompasses everything we've talked about: beauty, gold, value, theft, and justice. Klimt didn't just paint with yellow paint. He used actual gold leaf and gold pigment. The painting is literally a jewel.
And the story behind it is tragic.
It is. Adele Bloch-Bauer was a prominent Jewish patron of the arts in Vienna. She died in 1925. When the Nazis annexed Austria in 1938, they systematically looted the art collections of Jewish families. They seized this painting from her family. Stole it. The painting ended up in the Austrian National Gallery, where it became known as the Mona Lisa of Austria, a national treasure.
And the family fought to get it back.
Yes, for decades. Specifically, Maria Altman, Adele's niece, who had escaped to America. It was a massive legal battle that went all the way to the U.S. Supreme Court. In 2006, she finally won. The painting was returned to her. It later sold for a record $135 million. But the point is, the gold in that painting wasn't just decoration. It became a symbol of what was stolen and what was reclaimed. Gold has a memory.
That transitions us perfectly to the history of jewelry itself. Because a gem in the ground is geology, but a gem on a person is history. It's anthropology.
That's the codex idea again. Jewelry is one of the oldest forms of human expression. We have found a necklace made of snail shells in a cave in Morocco that's 150,000 years old. Before we had complex language, before we had cities, we were adorning ourselves.
And it wasn't just decoration, it was power, it was identity.
It was status, it was religion, it was magic. Look at ancient Egypt, the falcon pectoral found in King Tut's tomb. It's made of gold, lapis lazuli, and cornelian. It wasn't just pretty, it was a powerful religious amulet. It represented the sun god Horus. And think about this, the lapis came from Afghanistan, thousands of miles away. It shows there were extensive trade networks just for these stones, even 3,000 years ago.
Or the Renaissance, the Spanish caravel pendant in the notes.
A fantastic piece. It's a massive Colombian emerald carved to look like the hull of a ship, set in an elaborate gold frame that forms the mast and sails. That tells everything about that era, the age of exploration, the obsession with the sea, the plunder of the New World. The emerald was almost certainly mined by indigenous peoples, taken by the Spanish, brought to Europe, and turned into this trophy. It's a history book in a pendant.
And moving to the modern era, the pieces become iconic symbols of their time. The Cartier Panther.
Ah, the Duchess of Windsor's Panther brooch. It's a fully three-dimensional sculpture of a panther, covered in diamonds and sapphires, sitting on top of a massive 152-carat sapphire cabochon. It represents a shift in jewelry, from just being wearable wealth to being wearable art. It has personality, movement.
And Elizabeth Taylor. You can't talk about famous gems without her. She was the queen of diamonds.
Her collection was legendary. The Krupp diamond, the Taylor-Burton diamond, La Peregrina pearl. She wasn't just a collector. She understood the history and the power of these stones and the prices they command today. It's unbelievable. The Sunrise Ruby, a 25-carat Burmese ruby, sold for $30 million a few years ago.
$30 million
Yeah.
for a single stone. It brings us back to that fundamental question of value. Why do we assign this astronomical worth to these things?
Raises the question,
Yeah.
why? Is it just the sparkle, the rarity, or is it something more?
That brings us back to the beginning. The power we give to stones. They've been used as currency, sure, but historically they were also medicine and magic.
Oh, absolutely. The tradition of lapidary medicine is ancient. People used to grind up pearls or lapis lazuli and drink the powder as cures for various ailments. The Romans believed amethyst prevented drunkenness. The word amethystos is Greek for not intoxicated.
So they'd wear an amethyst ring and think they could drink more wine.
Exactly. Or drink from a cup carved from amethyst. And in the Middle Ages, stones were seen as barometers of truth. They believed if an emerald clouded over, it meant your lover was being unfaithful.
That's a high-stakes engagement ring. Honey, the ring looks a bit cloudy. Where were you last
Your
night?
lives,
Yeah.
indeed. But it shows that we have never seen them as just objects. We project our hopes, our fears, and our deep-seated desire for permanence onto them. We use them to say things we can't say with words. I love you forever. I am powerful. I am protected.
So we've gone from the unit cell, the tiniest atomic building block, all the way to the crown jewels. We've seen how the Earth cooks them in a torture chamber of heat and pressure, how we dig them up by moving literal mountains of dirt, how we cut them with mathematical precision, and how we load them with meaning and turn them into legends.
It is quite a journey, from the mantle of the earth to the neck of a queen, all in one object.
And I want to leave our listener with a final thought, something to chew on. We started with the VMPFC, that primal brain impulse. We talked about how the scientific facts of a gem, its refractive index, its chemical formula, aren't the same as the human truths we attach to it, like desire and beauty.
Right. The scientific fact is, a diamond is just carbon. It's the same stuff as a piece of burnt toast. The human truth is, it's a symbol of eternal love. The two are almost impossible to reconcile.
Exactly. And if we go back to that evolutionary theory that we love sparkle because it reminds our ancient brain of water, of life, it makes me wonder, in our modern world of skyscrapers and smartphones where we are further from nature than ever before, is our obsession with ice, with giant diamonds and bling, just a confused primate brain trying to find a drink of water in a concrete desert?
That is a haunting thought. Are we just hunter-gatherers who got lost in the jewelry department, still searching for that life-giving shimmer?
Something to think about the next time you find yourself staring at a shiny object. Thank you for taking this deep dive with
A
us.
pleasure as always.
Stay curious, stay well informed, and we'll see you on the next deep dive.